Okay.
All right, good afternoon. Welcome to our EC 590 seminar today. I'd like to introduce Bonhyun Koo. He's from South Korea. He graduated in 2017 from UT Dallas with his bachelor's in electrical engineering and has joined here at EC Illinois to work with Dr. Banerjee on his master's degree. Outside the lab, he enjoys traveling, but while he's in the lab, he's working on, he'll tell us today about distributed and scalable electromechanical actuation for Agile systems. So, welcome.
Thank you for the introduction. So today I'm going to talk about distributed and scalable electromechanical actuation for Agile systems. And I'd like to thank Professor Banerjee for being my advisor, and Mike and Mohira Sunyu. They were helping me setting up all the experiments and some part of simulation. And thanks to Scott for making manufacturing joints that I needed.
Good. Very good.
Yeah. I'm going to start with background. You guys may or may not know about MIT Cheetah 2. This version is especially designed for running and jumping. So let's watch the video, the first video. Can you click that? Yeah.
Okay.
I think that click should be in this monitor.
Do you want to come over and click it? It's not doing anything. Was that the only window? Did it look different before?
Yeah.
Oh, you have to do something.
Yeah. I think I have to do something here. Okay, so I'm sorry for the delays, and I may click it over here. Okay.
This is how the only movements are from the legs, but the body is very stiff. I want to show you the next movements of it. As you can see here, it tries to turn left, but it takes long resistance and it takes a lot of time to turn left. But this is the real running movement of Cheetah. As you can see here, when Cheetah wants to run really fast, it stretches its leg further and it pulls its leg back really hard. It is because its spine can bend upward or downward. But in this MIT Cheetah structure, it's impossible to do that.
I have two more videos here. This is Boston Dynamics Atlas humanoid robot which is recently released about like 2 weeks ago. Let's see this video here.
While you guys are watching, like, yes, like small little bit of balance. You can get there as well. But you still have three bodies, same as the MIT Cheetah robot.
So now let's watch the human backflip. As you guys can see here, human has spine, and he uses his spine to rotate faster because his momentum is he keeps his momentum, and the distance from his mass is shortening so that he makes faster velocity. This is the advantage of having a spine structure. And let's do. Okay.
And also having spine structure will give more balancing. Another application for the electromechanical actuation design is snake robot. This is from Carnegie Mellon University snake robot. They use a lot of DC servo motors to make this system move. But why not with electromechanical system that I propose? So we'll see the result of it. So I'm gonna start with proposed design. So animal spines like this cheetah and snake it consists of a lot of vertebrae inside. So each of them are colored by its excited direction. So for example, this red is vented downward, this green is vented upward, so that it can move like a wave, and it can move flexible. And another advantage of having spine structure is that it can be used as a tail like a cheetah, so that it can balance. When it wants to move forward, it can. When it wants to move left or right, it can balance its weight. This similar thing also happens in snake. So each cell has small displacement angle, but stacks of the cells will have more rotating angle. So this is the whole part of architecture of single cell and the whole architecture. How this works is that it is basically in single cell there are 2 E cores and 2 coils embedded. So when I excite top coil, their electromagnetic force will be induced in here. When I excite bottom coil here, the force will be induced here. So that's how this system makes the displacement. And as a big picture here, if I excite for A, B, C, only bottom coil, and if I excite top coils for D, E, F, G, H, it can make a curve like a snake. So this is why it is called distributed actuation. This is this shows the flux path and flux density. In this simulation, this one is coming out of the plane. So basically, the whole system works as using a same flux path. Because if I, in the case of not using not exciting coil B, the flux path would be like this, and the other flux path would be like this. So having distributed actuation will help each cells help each other that make the system working better. And this is the system architecture of a single cell. So there's a power module and power supply goes in, and this power module controls current. So that I'll show you how the current control can induce the force control that will need. And this power module will control 2 coils in this design, and there will be some sensing about it can sense about the angle of its displacement, and also from that displacement it can get information about the position of each core, each part it has, because we will have to consider about the whole movement and each part of the position of each part. So this is a single cell design for the first experiment. So this is distributed and scalable because it can be longer than this. This is just single cell, and I only controls current to make it move. And GaN devices will be used because it is more compact than the conventional silicon-based devices, and it has more thermal advantage. It has better thermal dissipation property. And core will be used as a heatsink because it is there and it is free to use as a heatsink. And one good point of this design, rather than having DC motor, is that DC motor has heat inside and it is enclosed, but this design is exposed, so it has better. I believe it is better way to release the heat and cool the system. This is the reason why I really want to use GaN devices, because I have really very limited area of the control circuit here. Because of this joint part, I only have this area. So what I'm going to do is I'm going to use 3 different PCBs, PCB layers, so that I can stack them up on one side. Or it could be like both sides. And another point is that GaN devices will be attached to the core so that it can be dissipated through the core.
What size scale is this?
This is about 80 millimeter and 40 millimeter high.
So pretty small.
Yeah. So for the theory part, flux density is defined by flux divided by area, and this R is reluctance. And force is, as you can see here, inducing force in here is proportional to the flux density squared. Is Ni squared term here, and this was originally here, but it went out here, and this is reluctance. So this is the equivalent circuit of this single system. This Ni is coil, MMF, and reluctance of joint, it'll be fixed, and reluctance of gap varies depending on its movement. So for example, now this is 2 millimeter, and when the right side is excited, it close to 0, and this side will go up to 4 millimeter. This is the MATLAB analysis. This is flux density saturation flux density here. And to keep this flux density, we need to increase the current. And keeping flux density means keeping the force maximum. And after a certain point, I don't want to go like too high for the current, and I calculated based on the design I was there. This wire is about 1 millimeter diameter, so I calculated as 5 m is as the like safety range. So the reason why I'm doing this is because I want to keep on working on this point, this critical point, through the whole system, like movement working. Because I don't wanna go down after this point using same current. So this simulation is done in ANSYS Maxwell. The exact size is same and material is same, but the only difference between the real and this simulation is that the permeability is fixed, and I didn't set the saturation flux density in this simulation. And this is the gap is in the figure is 2 millimeter. So this is the flux density figure of the simulation, and I measured this point exactly same as I did in the experiment. This is the simulation results. Since it doesn't have, I didn't set the saturation flux density, it goes up, and it varies because of the fringing effect. And I'll compare the simulation result and experimental result later slides. This is the experimental setup. Thanks to Mike built the structure and attached the DC motor. And I put the single cell structure over the load cell to measure the force. And because load cell outputs only small voltage, so I had to use differential amplifier to amplify the voltage to change from voltage to actual force that I get. So from this experiment, and also I was able to I can change the gap distance by using DC motor here, up and down, moving up and down. This is the experimental results. As you can see here, for about when it is 2 millimeter, it reaches about 430 millitesla flux density, which is pretty close to the material property that I used, the model, the ferrite-core. So the saturating flux density varies because of the fringing effect as well, as you guys saw in the simulation result. So this is a little bit a bit of information about fringing effect. As you can see in the formula here, if you increase the gap here, the fringing factor will increase, so that fringing effect will be very effective as I increase the gap. This is the comparison between simulation and experimental result regarding force versus flux density. It matches pretty well at the beginning at lower flux density, but it starts having error because simulation has fixed permeability, but the actual permeability will change depending on the flux density. This is the comparison between experimental result and simulation.
You go back one slide. What was the sensitivity of your force measurement? Like what kind of sensor were you using and what?
I was using load cell.
So but so you were measuring like a voltage to know?
Yeah, measuring voltage, and I calibrated to change that value to actual weight.
Okay. What did you do?
Same thing.
Yeah, thanks.
So here's the comparison between simulation and experimental result. It matches, since simulation didn't have the saturation flux density properties, so it has a lot of errors at the end, but at the beginning it has pretty similar values, since but as the current goes high, the actual core saturates, so it reaches saturation point. Here's the simple single cell movement video that I want to show you. So this is really simple structure. So let's say if I have stacks of these, like multiple cells, it can make movements right or left or as per. So in conclusion, I've tested the proposed electromechanical actuation design for Agile systems, to improve their balancing issues and make them more flexible. For future works, multiple cells will be tested because I only did the single cell testing, and movement control should be also considered because it is distributed system. So, and integrated sensing means it means that I do need to know about the position of each cell and what is the angle it has been moved, and something like the current or force that I need, and force which is happening in between each cells will be sensing. Any questions?
For a very nice presentation. I'm curious, I have a few questions, so I'll start with one and other people, but I'll protect maybe. So our vertebrae, as you showed in the beginning, we have multiple axes of motion. So can you envision how you take this one E-core and extend it to have other axes?
Yeah.
Can you kind of like walk us through how you're thinking about that?
So now it is only 2D motion, left or right.
Yeah.
But eventually I will have to use 3D motion, which requires three coils in one core, right? So that is like future work.
Okay.
Yeah. So before getting to that point, I want to test with the multiple cells of 2D motion.
I see.
Yeah. So it is possible.
So can I ask one? Anyone else have a question? Or you go. So have you thought, like there might be at this point, since you're at this point in the project, I'm curious, like the metrics of comparison. You might start thinking about metrics of comparison to servo motors. And one drawback I potentially see right now, although I've not done my own homework, is weight. You might end up having more weight because of the magnetics and the coils than perhaps those little servo motors might have, although you're getting more axes of motion. So there might be a question of like specific power, capability, trade-off between that and motion. You have a feeling that like will the weight aspect be scalable since you would need more batteries than I guess control these coils? Like, you think at the system level this could be integrated? I don't know where you thought.
So there's a comparison. There was in this present there was a comparison graph regarding robotic snakes. So there were it was comparing to about weight and forward velocity. So I think weight versus forward velocity with the robotic snakes I can put my system design into that graph so that I can compare which I will be located in that comparison graph.
Yeah.
Thank you.
Yeah.
But I at this point I don't know where I will be located in that graph.
Sure. It would be interesting to start thinking about the trade-offs.
Yeah.
As you start thinking, like where it fits in the bigger picture.
So if you make a whole snake out of the 4 by 8 millimeter, 40 by 80 millimeters, how you said the size was, that's going to end up being pretty chunky snake if you get very many components. Are you looking to shrink the size of it like as future work, or is your current size sort of your target, what you're shooting for?
First of all, the reason why I used 80 millimeter by 40 millimeter E-core is that it was available in the lab. So it was good for testing. And eventually snake robot is as an example, and it can be used, this system can be also used for the Cheetah robot or humanoid robot, so which requires bulky dimensions. Of course, yeah. So for snake application, it can be shrink down in terms of size.
Okay.
And to answer you in one more line, maybe we can make a paid snake if you want, or a Python. It determines the design space, whatever you want to make. The core he chose was based on whatever was there in the lab to test it out.
So in your experimental setup, I saw you spec. I mean, first of all, I think it's really cool. So topic is really cool, and thank you for the presentation. I really enjoyed it. So in your experimental setup, you stack these on top of each other. As you have more cores, and when you start to rotate these, isn't your center of mass I mean, how is this going to affect your force distribution? That I didn't understand that. Yeah, I mean, was I able to press my question? I don't know. So let's say that you have 5 cores stacked. So when you start to move these guys, what is this going to stay in balance and the force distribution in the coils, I guess those equations that you showed, are they going to be affected? And how are you going to come?
Yeah, I believe it's going to be effective, but for now I'm using only single cell, so now the setup is fine. But as you said, I believe if I have 5 stacks of it, and as it moves left or right, I will have to think about the new method to measure the exact force from it.
Okay. Also, so for example, if this is on a Cheetah, for example, as you described, I mean, isn't this going to carry the load of the Cheetah as well? So isn't then maybe you need I don't know how that's also load of the robot. I don't know. Maybe mainly it is I didn't really think of this, I guess, but I mean the legs of the robot is going to help to carry the load, but if this is on a Cheetah, I think the stack is going to carry some part of the load too. So I don't know how that is going to affect it. I mean, this is probably future work, but I was curious.
Yeah. I think the spine structure can also help the loading jobs, but also mostly I think the main job of it is the flexible movement to balance its weight and makes it move faster.
Yeah. So anyway, one way to think about it is sure your legs are going to carry the weight. But if you want to design something which is much more distributed, you might want to have sections which are bigger in the middle. So say for example, I have a stomach. I have a much thicker section there which supports the load, and then it thins out as it goes on the side. So you can have much degrees of freedom.
So they don't need to be the same size.
No, not necessarily. You just need to design those magnetics properly.
Really cool. And this make
you may have not have looked into this yet, but I think it is the next step. So as you go to the stack 2 and 3 levels, does the sequence in which you accomplish your motion play into the MMF that you need on each coil, either the current or the number of turns? Because it seems to me that if you control the snake appropriately, you can reduce the NI product that you have on some of the coils. Have you thought about that, or am I thinking correctly?
So you're right, because now the single cell design, it has 304 number of turns, but based on my calculation in MATLAB, the optimized value of the number of turns is it was about 270. So yeah, definitely it can be optimized. The reason why I used over that number of turns is because I wanted to get like more force from it.
And I guess what I'm getting at is, as you extend that, can you reduce the number of turns farther or reduce the current farther, depending on how you choose to control it, or the sequence in which you trigger the joints? It's just a thought, because as some of them close, the MMF field will add.
Yeah, but at the end, each gap supports 1 mmf. So you have to go back.
Are you correct? So each gap
Have to go back to few figures down, go back.
Yes.
Maybe you'll go next slide. So now if you see, we are excited coil A and B here. And forget about C, D, E for the timing. Say imagine C, D, E, those coils are not excited. So the loop will close between A and B, but just by itself. And each of these MMF supports now 2 gaps. One between A and B, you can see here, and one is here. So if we excite just these 2 coils, sorry to barge into your presentation, but this gap supports this MMF, this gap supports this MMF. So as you extend this, each gap supports each MMF. But coming back to your point, okay, if I don't need so much force down the road here, sure, you can decrease number of turns.
I guess what I was getting at is, if you were to sequentially trigger A and B, then you essentially literally scale your NI product. And therefore, does that?
Yes, you have increased your NI product, but you have now 2 gaps to get your flux through.
But once those close.
Oh, yeah, absolutely. Once it's closed, yeah, absolutely.
So that's what I was saying. So if you control this appropriately, can you reduce the NI product like later on down the state or something?
Yeah, but all the single cells will be controlled independently. So you can maybe for coil L 1 amp, coil B 0.5 amp. So it can be doable.
Okay, I guess I was just getting at, is there some trade-off between control and design?
Yes, absolutely. You can control the current, but number of turns is pretty much fixed at the design. Like you cannot change the number of turns,
Yes.
but you can control. You are supposed to control the current.
Yes.
You will have to control the current individually for each sections to make sure that whatever position you land up, you don't saturate the position.
So it's very interesting presentation. So I think one important thing for your work is the ability to scale up and scale down. So what do you anticipate to be the limiting factors when you scale up or down your design?
The main factor will be weight, because if I stack too much, like for example 20 or 30 cells in one system, they can damage the core, because core material, this material is pretty fragile. So yeah, in terms of weight, it can handle. And different core material can be considered, like iron core. Now it's ferrite core. Iron core has higher flux density property, but it has pretty much a bit heavier than ferrite core. So there's trade-off in terms of that. Yeah, it is good. Thanks for the comments. All right. Thank you guys for attending my presentation.